Okay, hey, how you doing?
Oh man, I am dogging today, but all things considered, doing all right. Just definitely not at on my sharpest.
Okay, well, we'll take it slow. We'll take it easy.
Right on.
I guess maybe we want to just talk a little bit about what we talked about last week because it has been a week. I don't know if you've had a chance to take a look through any of this since, but
A, a little bit, yeah. Um, and it is a bit perplexing.
is it a little bit perplexing?
Yeah, I don't. I'm definitely, but it kind of feels like repetitions again is going to be the thing. Like for example, the my map feels pretty straightforward. But then when we got into building the my filter and using the ifs and
Sure.
the if branch, um, and the cons the cons make sense. This part down here, I gotta say, it's not gonna let me highlight. Just yeah, it's the
Okay,
last line here. I think that's
that's the
I don't
tricky
know.
bit. Okay. So when you think about it, we can think about it definitionally, right? We've talked about this a little bit, but there's kind of a couple of ways to think about recursive functions.
Hmm.
And one of them is to think about them in terms of really sort of a definition. And that's probably the better way to think about them most of the time. A definition that involves sort of, well, in the case of, involves a reference to the procedure itself, right? And the other way you can think about them is to think about what's actually happening in terms of the call stack, right?
Yeah.
And so one thing about talk about the call stack, it's called a stack because in most programming language implementations, there's a data structure used to sort of keep track of the environments, which is called a stack.
Mm.
That's actually not true in Racket. Racket is a little bit unusual in that regard. That's an implementation detail that we don't have to worry too much about, but you can think about it metaphorically as being very much like a stack.
Hmm.
And this is true not just of recursive procedures, but of any procedure that calls another procedure, right? Because we've talked about there are environments, right? A procedure has sort of its own environment where it has bindings.
Yeah.
And it also has kind of a place where it is in the execution of that procedure, right? That's also a thing. It's like, okay. And so when you call another procedure from within a procedure, you sort of suspend execution of the procedure that you're in, and you go into that other procedure and you start executing it from the top.
Hmm.
And at some point, you get done executing that other procedure and you have to pop back up into the procedure that called it and finish doing what you had to do there, right? And
Right.
you have to restore the environment because you changed out your environment for a new environment
Hmm.
when you went in there, and so you have to restore it. And if you call a procedure and it calls a procedure and it calls a procedure, then you're doing that a whole bunch of times.
Yep.
And you could think of this as being like a stack of cafeteria trays, right? And so when you pop back up, trays come off the stack in reverse order from how they went on, right?
Hmm.
So it's still, even though Racket doesn't actually use a stack as its data structure for doing this, it's still a good metaphor for what's actually happening. And you can think of this as being kind of analogous to stuff that happens in real life. Like, you're doing something and on your computer and you see that you got an email that you have to respond to. So you're like, okay, I'm gonna, go and start dealing with this email. And while you're doing that, I call you on the phone. And you're like, okay, I better answer this. And so, you pick up
Hmm.
the phone and you start talking to me and you finish talking to me. And then you're like, okay, I'm going to go back to the email. And you go back to where you were in writing that email and you finish doing that. And then you pop back up. And
Right. Well, especially if the phone call had to do with the, you know, information that you're using, that you needed for the email.
right. But either way, right, it's just like, you kind of, you keep interrupting what you're doing. And then you kind of like, hopefully, if you're sort of, if you are an organizationally minded person, you kind of like recall where you were with stuff and pick it back up and finish it. And then you're like, okay, what was I doing before that? And you pick it back up and you finish it. And so the same kind of thing is happening with procedure calls. And
Yeah.
so,
Yeah.
so that's just, a way of kind of thinking about about what's happening as you're making these calls. The same thing is actually true when you're making recursive calls. It's a little bit, potentially a little bit more confusing, right? Because it's the same procedure. But each invocation of the procedure is its own invocation. And each invocation of the procedure gets its own environment, right? Which we'll note that it has to, because, you know, I mean, we can look up at even just at factorial, our simplest example, right? X is different in every invocation of this, right? It's one less every time you invoke this procedure. So it's got its own environment where X is, right? X isn't being changed, right? Within any given invocation, X just remains the same. It's just that name is bound to whatever that procedure got called with. So X isn't being modified. But you have new invocations that have their own environment, and X has its own binding in each of those. Okay.
Yeah.
So thinking about what's happening in terms of like the chain of procedure calls that gets made and what values they get is one way of thinking about how a recursive function works. The other way, though, is just to think about it in terms of a definition. And in a lot of ways, that's easier because you really don't have to, you know, now this does require a leap of faith. You have to just kind of have this leap of faith that the recursive call does what it says it's going to do.
Yeah.
Right? So when we look at factorial, sort of a definition of factorial is that the factorial of x is x times the factorial of x minus 1. That's a definition of factorial. It's not a complete definition of factorial, because for it to be complete, you also have to define something that stops that, right?
Yep.
That says, okay, if x equals 0, then factorial is 1. And once you have that base case, that is a complete definition of factorial, right?
Yep.
So if we look at my filter, we can think about this definitionally, right? So, and we have three cases here.
Yep.
There are three cases and also three branches of the if. And like we were talking about last time, you have to remember that for any given sort of list and procedure that gets passed to it, each of these lines, because only one of these lines is going to execute, right? One of them is the empty list. That's the first thing that can sort of execute that the procedure can evaluate to, right? And then one of them is line 39. And one of them is line 40. And in any given invocation of this procedure, only one of those is going to be evaluated. And the entire procedure is going to evaluate to whichever, you know, whatever the line that got evaluated to evaluates to, right?
Yeah.
That's going to be what the whole procedure evaluates to. And each procedure needs to actually return a correct thing. Each invocation, right? When my filter is called with, you know, proc and list, whatever those might be, the procedure needs to evaluate to the answer to that, right? What we actually want from that. So, I mean, you recall what filter does pretty much, right?
Sure. Yeah. I mean the special form filter, or maybe it's not a special.
It's not, I don't think. I think it's just a procedure. But like what we're trying to do here, what my filter is trying to do, right? That's clear to you what it is we're trying to do. Right?
I don't remember if we must have run that because we were starting to move on to. Yeah.
But you recall what it does, right? What it's supposed to do and what it does.
I think take filter is a procedure that takes two arguments. Does it take a predicate?
Well, no, the procedure is the predicate.
Okay.
And that procedure actually only takes one argument.
Just the list?
No, it takes an item from the list. It takes any item and returns true or false, but what it's going to be passed are items from the list, right?
Oh.
So an example of this, if you go down into why is interaction disabled?
I think it's because of line 42, or why? I don't.
Okay. So here's a trick. You know what? Actually, you can just delete line 42. Actually, we don't need it. We may kind of go back to taking a look at that at some point, but we can just start from scratch. So yeah, hit run. So here's an example of. So if you call my filter with odd, which if you recall ends in a question mark, and then a list containing some odd and some even numbers. Right. So it takes the list and it filters it so that the only things that remain in the list are things
Mhm.
for which the predicate returns truthy. For which it returns true, pretty much. Odd does return true or false. Right. So let's be clear about what it is that we're trying to do. So how can we define this? How can we define my filter sort of? How can we define filtering in terms of filtering? Right. That's kind of our question with the recursive call. So we can look at these three things. We do need a base case, right? And so
Yeah.
if you filter the empty list, you get the empty list, right? That should be pretty clear. So the question then becomes, what happens if you filter a list that is not empty, that has elements?
Yeah.
And so this is where the definitional part of it comes in, because you can actually say, well, it depends on whether the first element in the list passes the predicate or it doesn't pass the predicate. And so just for concreteness, we'll talk about odd, right? If the list begins with an even number, how can we define the result of filter in terms of filter? What is the definition of that?
False.
No. What is filter? What type of thing does filter evaluate to?
Oh, to a list. So,
Right.
so it would be, um, it'd be the first of the lists evaluates to an empty list. In
No.
that, if the first item was false.
It doesn't, though. If I have a list, so let's say that I have the list 4361, right?
Mm-hmm.
And I'm filtering that on odd.
Mm-hmm.
What does that evaluate to when I filter that list on
Oh,
odd?
the whole list.
Yeah, that's what filter does, and that's kind of what I'm saying. Like this line that gets evaluated has to give you the correct answer for this invocation of stuff. Only one of these lines is going to get evaluated. And that line has to give you the correct answer to the whole problem.
Uh-huh.
Okay.
Yeah, it would evaluate a list containing 3 and 1.
Right. Okay. So it's not the empty list for sure. I mean, it could be if there were only even numbers left in the list. It could be, in fact, the empty list, but it's definitely not. The answer isn't like just the empty list, right?
Yeah.
We want to define it in terms of filter, right? In terms of, and generally speaking, because when we do these things, we were talking about like recursion on cooters, for instance. What we want to do is define it in terms of the first element of the list and the result of filtering the rest of the list. Right? That's pretty much always how these work, right? So how can we define filter in terms of those two things?
I mean, I guess that's what I was trying to
Okay. So I'll give you a little bit of a nudge here. It is actually what this last line says. It is like if you have 4361, for instance, there, the definition is just the result of filtering the rest of the list, right?
Whether the first number were odd or even.
No. We're only talking about this last case, this last line. This is when it's even, because it's two different. It's these are two different cases.
Yeah. Okay.
So they're different things. It is a different thing if the first thing in the list is odd versus if it's even. We're talking about the case where it's even.
Yeah. So the cons is only if you were actually, if the first item is true, is going to be included in the list.
Right. So the definition, it's a two-part definition here. And we already had kind of a two-part definition involving the empty list, but we've moved on from that to like a list that has elements. And so it's a two-part definition. And I was just talking about the second part, the part where it passes the predicate, but we can where it fails the predicate, but we can talk about and I may have gotten a little bit confused about the truth values there. I was using the correct thing in terms of 4 does not pass it. So I was talking about line 40, and I may actually have been a little confusing there. But let's go back and we'll look at line 39 first, and we'll just look at them in order. So The really important thing to remember here is that what we're trying to do is come up with a definition where the definition is entirely in terms of the first element in the list and the result of filtering the rest of the list. Because that's pretty much always how these sort of recursion on Cutter's things works. And so the definition of that is a list, in the first case where it passes, like let's say that it's 5. The definition here is a list that contains 5.
First of the list.
The first thing in the list, and every other element of the list of the result of filtering the rest of the list, right?
That's the recursive part.
Well, it's recursive in both cases, in both branches. That is the recursive part, though. Yeah.
Yeah. But in line 39,
line 39,
that's the recursive. Yeah.
That's the recursive bit.
Yeah.
Right. And so you just kind of you don't have to even think of, let's just assume, though, that we just assume, filtering does what it's supposed to do, right?
I think that is the thing. I mean, it feels like a leap of faith is a good way of, and I'm sure that, after you do it a bunch of, you understand the actual mechanisms better. I mean, that's kind of where I'm at with it, It's kind of okay, I'm starting to understand the mechanics of it a little bit better, but it's still not totally
It's the leap of faith that's the important bit, because it means you don't have to understand the mechanics,
right?
To understand this definition, right? All you have to say is you just assume that it does what it's supposed to do, right?
Yeah.
If all 3 of these branches have correct definitions, then the entire definition will be correct.
Yeah.
And so this is kind of what it comes down to, is that I'm just trying to think about how to put this best. But definitionally, if the first thing is odd, for instance, we'll keep using this concrete example, then it is the result of consing the first thing in the list to the result of filtering the rest of the list. Do you see that that's a perfectly valid definition of this? Assuming that filter does what it does. And then if it's even, then the result of this is simply the result of filtering the rest of the list.
Yeah.
Right?
Yeah, because you essentially threw out you knew you weren't going to return the first, so it's just what remains in filtering that.
Right. You just have to filter.
Which then is looped, kind of at least the way I think it conceptually loops you back, because you could still have something that has, how many ever items, and you got to go to the first thing again and look at that, right?
You do. And that's the other way of thinking about this that I was talking about, right? Which is to actually think about the function calls that get made. But notice that in terms of this thing where we're talking about definitions, we don't have to think about that.
Right.
Right? We're just thinking about, definitionally, what is it? We just assume. We don't have to care. So here's a good example of this, right? You could define this procedure where instead of having a recursive call here, you had an actual call to filter, right? Which is in Racket, right? Do you see that? And that might make it a little bit easier for you to see how this definition works. Change that briefly into, calls to filter, the 2 recursive calls into calls to filter.
I can do that. I can go back and edit my lines here. Yeah, of course.
Yeah. In the top view, you can.
And then I take out procedure too, right? It would be just filtering the rest of the list.
No. I mean, filter also has to take a procedure.
Oh, right.
How does it know how? Yeah.
I guess I can just mine.
Okay. So try taking a look at this and see if this definition makes sense to you, right?
Yeah. I mean, but I mean, I think I was getting it the other way too. I mean, I definitely understand that we were constructing the filter. That my filter was the same as filter. We're just using, or that's at least what we're attempting to do.
But note that the thing here that's a little bit different is there's no recursive call now. This is no longer a recursive procedure.
Right. Yeah.
It doesn't call itself. And it should be really, really obvious that this definition is correct. Right? The things that kind of confuse people about recursion often is sort of the recursive part of it, right? So here
Yeah.
we have something that's not recursive at all. It should be pretty obvious that this is a correct
Yeah.
definition.
Well, because I don't have to know exactly how filter works, as
That's right.
opposed to my filter, I had to actually
But
make sure
see,
that it was going to do what I
yeah,
wanted it to do.
but that's the
Yeah.
trick about
Mm.
it that I'm kind of talking about here about these definitions is that assuming that you got your base case right and assuming that you got the other parts of this right, you don't have to worry about how it works here either.
Yeah.
Right? That's
Yeah.
the leap of faith that I'm talking about is to treat my filter the way that you treat filter. You already know that filter works, right? You
Yeah.
know that filter works. And so where doubt is creeping in with you a little bit is that you're unsure if my filter works.
Yeah.
What I'm saying is when you're writing these definitions, you have to assume my filter works for the purpose of
Yeah.
writing that line, right? Anyway, we can turn it back into my filter at this point.
Cool.
Does that clear? Does that help at all? Does that clear
Yeah.
it up at all? Because I mean, you were saying that it was kind of perplexing, and I'd like to.
Yeah.
Yeah.
Yeah. No, and some of it is specific. It's just, it's like, I can see that it's the same, that it's the same kind of principle or the same type of basic, thing going on in each of the different examples, between my filter, my map, some, etc. But it is a little bit different. So I think the different iterations are, just because of the procedures that we're building, you know, um, including if here, and well, I guess ifs in all of them. Yeah, right, of course.
You do have to, right, because you have to differentiate between your base case and
Yeah,
at the very least you have to differentiate between your base case and not your base case.
right. Yeah. Yeah, no, I think I do. I think I feel like I've got a pretty good grasp on it. This, I'm sure that, there's some of that's still tickling my brain a little bit, but I think it'll just become more evident as I do more of them.
Yeah, I mean, and we'll see, I think, in a little while. We'll take a look at folds, and folds sort of generalize some of these patterns at least.
Mm. Fold, FOLD, you're saying?
FOLD, yes.
Uh-huh.
Also known as, in some languages, reduce. Although, well, there's more than one type of fold. There's left folds and right folds. And in fact, we'll see some new recursive patterns, and we'll see that some of some of the procedures that we're writing correspond to left fold, and some will correspond to right fold. But we haven't really quite gotten to that point. We will talk about tail recursion at some point. However, last time we were looking at SICP.
Yeah.
I'm thinking that maybe we, assuming that you're sort of reasonably confident in basically understanding how the recursion is working, right? Like that's still kind of in your head. I think we maybe want to just take a look at SICP. And I know you can only go for a couple of hours tonight, so we'll see what we can. We'll see how far we can get in that.
Cool.
Yeah, getting a little bit of lag here, but
Oh yeah. Yeah. We will. She's gone. Okay. Oh, I did. I was looking at the HTML. I don't know if it's. I guess the HTML would be better. It probably wouldn't lag as bad.
yeah, I mean, generally speaking, I just prefer to read things like this in HTML as long as it doesn't have anything in it that can't be well formatted in HTML.
Yeah, that's where I was. Now, I feel like we were looking at conditional expressions and predicates, but we had gotten to, we were just,
square roots by Newton's model.
we were just starting to
Method.
start. Yeah.
Yeah, so we were just starting to talk. So Newton's method, as I said, is like Newton's method is more general than just finding square roots. But we'll look just at there is a more general form for Newton's method, but we'll look just this is what they're doing is the concrete form of using Newton's method for the square root function.
Mm-hmm.
And Newton's method is just basically a way of finding roots of functions, and we talked about that a little bit last week. I don't know if you recall that. We don't have to worry too much about it. We'll just kind of take it on faith, though, at the moment. Then we can watch this algorithm work here, right? When you're looking to find a square root. So
Yeah.
There's an important point here, and this is something that comes up in algorithms, where you have an algorithm where starting from an approximate answer, you have a step a guess is what they're calling it, right? You have a step where you can make the guess better.
Yeah.
And if you have a step that always makes a guess better, unless the guess is the actual answer, right? You can keep applying this procedure that improves the guess over and over again and feeding it, you feed the new guess to the procedure each time. So you have a guess 1, and you feed that into the thing and you get guess 2 out of it. But since this thing makes guesses better, you can take guess 2 and feed it in, and you'll get an even better guess, which is guess 3, right?
Yeah.
Does that make sense?
Oh yeah.
Okay. And so now the thing is you're not guaranteed with these things that they will ever actually arrive at the exact answer. And particularly something like this, square roots are not exactly, some square roots can be exactly represented in a computer, right? The square root of 4 is 2, and 2 can be exactly represented. However, the square root of 2 is not even a rational number. It's an irrational number. So it can't be exactly represented in a computer. So you're never going to get the exact answer out of this. But you can make it better and better and better. And so if you have a way of knowing how far it is, the answer that you've gotten, the improved guess, if you have a way of knowing how far it is from what you're looking for, if you have a way of assessing it, then you can just say, well, keep guessing until we're within some tolerance of it, right?
Mm-hmm.
And
Like some hundreds or thousands or something of it.
yeah, and if there were a way, of course, to figure out exactly how far the guess were from the correct answer, then you'd be able to figure out the correct answer. So it's a little bit more complicated than that. But we do have a way of, we have to have a metric that basically that can just, that tells us if one guess is better than another. And so we have that metric here. Well, they'll talk about this in a minute,
Okay.
but you can see that so they work an example of this, right, for finding the square root of 2. And what they're saying is the procedure for improving the guess is that if you have a guess, this is in the paragraph right above the table, right? If we have a guess y for the value of the square root of a number, we can average y with x over y. And that gives us our better answer, our better guess. So is it kind of clear when you look at what they're doing here? What's happening?
Okay, so 2 is the thing we're working with, and our guess is, the initial guess is 1. So maybe get a better guess.
Right. So 1 is the y in this. And so x will always be 2. Y is going to change in successive steps of this, right? As the guess gets better.
So when we know in this first guess here that, we came back with 2, so that didn't get us any closer.
Well, that's just the quotient. Note that that's just the quotient here. Because you have to average, do you see what they're saying? You have to average y with that quotient.
Oh, okay.
Okay. So they're doing a little bit of algebra here, right? But do you see that if you want to average 2 over 1 with 1, that 2 plus 1 over 2 is how you would do that? Right?
Yeah, okay. Yeah. You're basically adding 2 and 1 together.
Right.
And then using the x again.
Actually, you're not.
Oh no, you got
So
two.
you
You
have two
have two.
things. You're
Yeah,
yeah,
you,
you're averaging two things.
right. So
So you get
you're
1.5.
averaging. Okay. Yeah,
So
and then you're
you
using
feed that
x
back
again.
in, right?
Uh huh.
And you get a quotient again, the quotient of x and y there, and right. But you're using the new y. So when you average x with the new y, you get 1.3333, right?
Hmm. And then you add that to the y, or yeah, and divide that by, and then average that.
Yeah. Um,
But how do you know you're getting closer?
well, Newton's method does in this particular case, at least with square roots. Um, so you kind of just have to know that about Newton's method, I guess. Although the thing about it is that we do have kind of a metric for this as well, which we'll look at, right? Like we'll look at that, what good enough is. But so let's take a look at this first thing that they write, this define square root iter guess x, right?
Uh,
It's the
oh,
it's the
up
first
top.
block of code. No, it's down
Right.
below. That thing up top is them just showing a sort of nonsensical thing, right? That's not real code.
Got
Okay.
it. Right. Yeah. Define the square root. What's iter?
Iter, it's an abbreviation for like iteration,
Okay.
or
Yeah.
yeah, iteration, iterative, that kind of thing. And like iteration is a word that comes up a lot in computing. But do you have a feel for what iteration means?
Multiple iterations. It's like.
It's to do something repeatedly, essentially,
Mhm.
right?
Okay. Yeah.
So what they're saying here is, and this is our base case, is good enough, right?
Mhm.
That's our base cases. If our guess is good enough, and we haven't written good enough yet, right? Just so
Yeah.
again, just trust for the moment that good enough does what it says, right?
Mhm.
So if the guess is good enough, then it's just guess, right? That's the definition of this, you know?
Mhm.
Okay. What if the guess is not good enough though? If we have to continue to improve it, basically, right?
An improved guess by.
So you also have to just assume that improve does what it does. Although what improve does is what we were just looking at, right?
Yeah.
Okay. But
But I don't see the averaging. I don't see in this. I mean, is this
that's what improve does,
okay?
right? That's the point to improve. So they're just sort of, they're showing you the skeleton of this, and there are two helper procedures that they're using. So this is getting a little bit more complicated than the recursive procedures that we've written, partially because, and you could write this all out without writing separate procedures for this, right? You could just write out the code for good enough and improve, but it makes the code clearer and easier to understand if you write some more procedures. So, right, so that you don't have to see the math written out in your way there. You just say, okay, improve guess X, and you just say, okay, for the moment, when I'm on this line of code, I'm going to assume that improve does what it says it does. When
Yeah.
I'm writing improve, I have to make sure that it actually does. But when I'm not writing improve, when I'm just using improve, again, there's a little bit of this is a little different than the recursive leap of faith, but it's an important one, which is, when you're writing code and you have some other procedures that you've written, you assume that they do what they're supposed to do, right? You can't be thinking about whether they're correct while you're trying to get this one correct, right?
Mhm.
Okay.
Mhm.
So, but do you see that this, if we assume that good enough does what it's supposed to do, and if we assume that improve does what it's supposed to do, does this procedure make sense to you?
Yeah. Yeah. I think I'm still getting used to the different lines. I'm like, why is this one just hanging out here? But if I put it back up here where I'm more used to, just when I was kind of writing everything out all in one line.
Right. It's just
Mm,
it's just the second argument to square root iter, right? Square root iter takes two arguments. It takes guess and it takes x. And the guess changes, but x never changes, right? If we're looking for the square root of 2, that's what x is 2. And it never changes. We're always still looking for the square root of 2.
yes. Hmm. It's to improve. Yeah, I don't know. I think we just like I'm like I don't feel fluid enough or comfortable enough with it. I'm like there's no way I would be able to figure out, you know, writing this myself. I'm like, why is this X over here at the end of it? And like, I don't know. I think I'm still thinking about it very um, functionally or whatever the word was rather than definitionally. So
Yeah. Well, so let's think about it this way, right? We have to call. So square root iter takes a guess, and then it takes the thing as to the square root of a number, and then it takes the number for which we're looking for the square root of, right?
yep.
That's what it takes. So
Yeah.
we want to repeatedly call it essentially with better and better guesses until
Yeah.
our guess is good enough. On each of those calls, it has to take a guess, which should be a guess that is better than the last time, right?
Mm-hmm.
That's what's moving us closer to our base case. And we have
Mm-hmm.
to be sure that we are indeed getting closer to our base case, or else, we're going to loop forever.
Yep. Yep.
But square root iter also has to take the thing that you are attempting to find the square root of,
Yeah.
right? So when
Well,
I'm sorry,
that's X.
that's x.
Yeah.
So
Yeah.
that's, in that last line, when we make the recursive call, we have
Oh,
to call it with an improved guess, but we also have to call it with x.
yeah.
X
Yeah.
is still
Okay.
in the functional signature. And that's really all that's happening there. And it's on a separate line because you often do that in Scheme. You will say for a procedure that takes multiple arguments, you'll put each of them on their own line.
Mm-hmm. Mm-hmm.
And that can kind of make it a little bit clearer. Because we started off working so much at the REPL, where it's a little bit of a pain
Yeah.
to format things that way, we kind of put more on a single line there than is typically the case when you're writing code.
Yeah.
If you, I don't want you to go back to Racket right now because just lag basically. But if you look at the procedures we started writing up in the top definition window, you'll see that we're starting to do that a little bit more.
Yeah. Yeah. No. No. I get that part.
Yeah.
Yeah. It just looks a little bit different. Some it's acclimating.
Right.
But I was kind of like being like, why does that X have to be? That makes sense because you still are including the the number that you're actually working with that you're attempting to square.
Right. Right. Yeah. I mean, because we don't want to reach out into the enclosing environment. Another way you could write this kind of function, I suppose, is to have a variable in the enclosing environment at the top level, right? That
Mm-hmm.
that had the value of x, and then you could just call this with guess, and it could reach out into the enclosing environment, which is always there, right? And be like, okay, and we'll see something called closures later on that lets you write this in a slightly nicer way so that you don't have to keep passing the x through. But for right now, we don't really have the tools other than putting it out in the enclosing environment, which we don't want to do. We don't want to be reaching out into the global environment for it.
Yeah. Well, we want it to be able to change. We want to be able to do it more than just two. Or I mean,
It's true. There is a way to change bindings within an environment, though. And we haven't really seen that yet because it's a somewhat dangerous thing to do in some respects. Although there's a lot of programming languages where that's the basic model of how you do things. And we'll talk more about that eventually. That's actually a pretty big topic. But for right now, we just don't want to be reaching into the thing, right? And so, I mean, I would say take another look at square root iter, and really, I would say try to get to a point where you're pretty reassured that this, assuming that good enough does what it does, and assuming that improved does what it does, where you really feel like you understand this procedure. And if you don't at all, if you have questions about it, then point them out, and we'll look into it.
yeah. I mean, I don't know. I mean, it's. I don't think I'm gonna. I think I understand it. Yeah, I think I understand it decently.
Okay.
I don't really have any specific questions. I feel like I kind of have to. I mean, I guess the question is like, improve is not defined. Good enough is not defined.
Right. Well, we're about to define those things.
That's okay. That's what I figured. Yeah.
And you can see that if you just look a couple of lines down, they define improve.
Yeah.
And it should look really familiar to you. This is what we were looking at up above, right? Now, of course, now they have something called average, right? And you just have to assume average does what it's supposed to do, right?
Mm-hmm. Mm-hmm. And we're averaging guess by yeah, because average is going to be two values added and divided by 2.
Right. But you don't have to worry about how average works if what you're looking
Yeah.
at is improve. You just have to say average does what it says, right? Like, just assume that it does. When it's time to write average, you have to make sure that it really does do what it's supposed to do. But it's really kind of important. I mean, this is kind of an important thing, which is that you limit the scope of what you have to think about at one time. Do you see that?
Yeah. I was looking at this next part of divide x by guess.
Okay. So that's actually literally the definition that we were looking at up above, right? And you can see it kind of written out in English in the paragraph right above sort of the table, the worked example, when they say that when we have a guess, y, we say that the guess, y is our guess, and x is the number we're trying to find the square root of, right? When we have a guess y for the value of the square root of a number x, we can improve the guess by just taking the average of y with x over y.
Yeah.
Right? So if you look down at improve, you'll see that this is just that translated into scheme.
Yeah.
The average of guess and x over guess. Right? And guess is y here. That's the only difference. It's a different name.
Right. Yep.
But otherwise, it's exactly the same thing. And then they define average here. And, again, because we are kind of missing some tools, you'll note, for instance, we've seen that plus can take multiple arguments, right? It can take an arbitrary number of arguments. But we haven't seen the tools. We don't know yet how to define a procedure that can take variable numbers of arguments, right? But for our purposes, it's fine. We only ever have to average two things here. Two numbers, right? So they just write an average function that just averages two numbers, right? And you can see that again. That's just
that's straightforward.
Very straightforward. That's just what it is. Now, good enough is another question, and
yeah, that does seem like the complicated one here.
Okay. So they're saying, you can read what they say here, which is probably a good idea. The following will do for illustration, but it is not really a very good test. See exercise 1.7. And the idea is to improve the answer until it is close enough so that its square differs from the radicand by less than a predetermined tolerance. So you see that, like, the closer we are to the correct answer, the closer its square will be to what we're trying to find the square root of, right? Does that make sense?
The closer, and improve the answer until it's close enough so that its square differs from the square of the answer.
The square of the answer. So, all right. So here's a very concrete example that may make this kind of a little bit clearer. What's the square root of 4?
2.
2. Okay. What is 2 squared?
Oh, the square, not the square root. Right. Yeah. We just multiply it and
you multiply it and see how different it is from the number you were trying to find the square root of.
Yeah. Sure.
And if it's 0, then you know that you found basically the exact correct answer, right?
Yeah. Well, that's how I find square roots of stuff that I don't. I just like, it's probably pretty close to that, and multiply it, and I'm like, that's not.
This is kind of the same procedure, except that they have a better way of improving the guess than you do.
Right. Yeah.
That's kind of the trick here, is the better way of improving the guess.
Yep, that makes sense. So that's where you can use, because I mean it's an inverse. It should be an inverse, property, and so if you're getting closer,
the square root of the square of the square root of a number is the number, right? Did I say that? Did I say that right? This stuff always, when you start doing inverses of things, it always gets a little bit hard to think about. I have to do a lot of this kind of stuff involving like matrices and stuff, because when you transform points in 3D space, there's a lot of matrix multiplication, and then there are a lot of reasons that you have to think about the inverse, because sometimes you want to transform things and sometimes you want to untransform them, and it can get a little tricky keeping track of. Right? So whenever you're dealing with inverses, you have to kind of be quite careful about it. And, I don't know. I mean, I get this wrong sometimes, and I have to like rethink it. It happens. And then, so
Okay.
they do want to give this kind of an interface where the thing about it is that you need to start with some guess, and we're just always going to start with the same guess, 1, right? I mean, there might be a way of coming up with a better initial guess, but it doesn't really matter all that much. And
square is already defined in the top level environment.
yeah.
Yeah. And what's abs again?
I'm sorry, what? Oh, the absolute value.
Okay. What's I'm not that that's I know we covered it, but it's not I'm not
Okay.
ringing a bell.
So the absolute value of a number is just how far away from 0 it is.
Okay, right.
Okay. So if it's a positive number, it is that number. If it's 0, it's 0. And if it's a negative number, it's, I mean, you can think of it as just like knock the negative sign off it, and it's that number flipped around 0, right? It's just how far it is from 0. It's absolute value.
Great.
Because here's the thing: our guess could in theory be either its square could be greater than the number we're looking for, or it could be less than the number that we're looking for, right?
Yeah, exactly. And either would be satisfactory. Okay, that's why they use abs rather than x.
Right. You have to. Well, what it is that what we're doing is we're sort of subtracting. We're subtracting. Let's see. We're subtracting x from the guess, right? It doesn't really matter which order you do these in, actually, but they happen to be subtracting x from the square of the guess, right? And so that could be a positive number or a negative number, right?
Yeah.
But we're only interested in how far it is. We don't care which side it fell on.
Yeah.
Okay.
Yeah.
And so this is a good little thing to tuck in your back pocket, right? We're looking for distance, and in the number line, distance is really, really simple. It's you subtract one number from the other, and then you take its absolute value, and that gets you its distance. It's a little more complicated, like in the plane. It also actually involves a square root, but we won't worry about that right now.
Okay. Yeah, this makes sense.
Okay.
You're taking, but isn't that not good enough as guess x is the greater
well, it's saying less than, right? Well, maybe I'm not understanding what you're saying. Go on.
Yeah, no, I thought this is the I know I'm back to 6th grade. I thought that was greater than.
No, it is less than. So you know how I was taught this, which I never forgot this when I was like in 1st grade, is you think about it as a greedy duck, and it wants to eat the larger number, right? So okay, so less than, right? If you have 1 and then you have 2 on the other side, 1 is less than 2, so the greedy duck wants to eat the 2. Right, so it's facing away. It's facing to the right. I don't know.
I do the worst one. I don't know. Yeah, no, it is something like that. But I guess all the numbers are to the right of it, though. So
well, in this case, right. In Scheme, it gets a little more confusing. You can't rely on the greedy duck, but it's the same as it would mean if this were, if this were an infix operator. That is to say, if it came between 2 numbers.
Yeah. Okay, so that I'll get used to that.
Yeah. It's
less of these 2. Yeah. And then this is
okay, so now we have define square root of x, and this is the thing. They don't want you to have to put the guess in every time, right? We want to just have, if we think about what we want a function that calculates square roots to look like, we want it to be a function of 1 argument, which is the number we're trying to find the square root of, right?
Yeah.
Okay. So, and this is sort of why they named that square root iter up at the top. They don't want to name it square root because they actually want to write a square root function, right?
Yeah.
That only takes that 1 argument. So square root iter has to have its own name, and it's pretty common. I think for these guys, they very often use iter to, they'll have an outer function that calls a recursive function, and perhaps adding in some arguments, but then they'll have the interface to the user will be outside of that. And so the inner thing that isn't the interface to the user, because you're not meant to call square root inner yourself. You're meant to, if you're a user, right? You're just meant to call square root.
Yeah.
So the inner part will have an iter tacked onto the end of it.
We'll have a what tacked on in the end?
An iter.
Iter. Yeah,
Yes,
gotcha.
just as that's a square root iter. So,
And it's not like it really slows it down all that much because fast or whatever. I mean, it has to do, like if we were doing a square root of 100, it's gonna get, and we started at a guess of 8 instead of a guess of 1. It's not like it's all that much faster.
yeah, it actually won't make very much difference. I mean, it may actually be faster to just do this than to have a procedure that comes up with a better guess, right? So,
Yeah.
but also we're not too tremendously concerned about performance right now, as long as what we're doing isn't actually stupid, right? Like, and that's actually, so there's a kind of famous aphorism by Don Knuth where he said, premature optimization is the root of all evil. And I think we even talked about this once. This kind of came up in conversation. And of course, that premature there is pretty important. You do eventually have to optimize things. How much you have to optimize them is very contextually dependent, but it's really important to worry about correctness before you worry about speed. And one thing that is very true is that the more heavily you've optimized your code, the harder it is to understand your code. And the harder it is to get it right, because it's hard to understand, right? The harder your code is to understand, the harder it is to get it right. So you typically want to get your code working first, and then worry about making it fast. And it may be that your first try is just fast enough. This is an iterative procedure, a little bit like this one, where you have a good enough function. You're like, is this good enough? And if it is good enough, you're like, okay, I'm done optimizing. And if it's not good enough, you optimize a little bit, and you say, is this good enough, right? So it's kind of similar.
Yeah.
But it's just kind of an important thing. However, that doesn't mean that you should do like dumb stuff, even when you're in the stage of not caring very much about performance. Right? I mean, if there's two different ways of doing something and one of them is a lot faster than the other, and they're pretty equivalent in terms of how easy they are to write and how easy they are to understand, like, don't do the slow thing, right?
Yep.
Okay.
Kind of interesting too, like seeing it apply, like the answers you get here.
I'm sorry?
Oh, I'm just looking at the next part down here. The answer they get for square root to 9. Good enough.
Good enough. But do you see that in good enough, we've coded in this number, 0.001, right?
Mm-hmm. We could add some more zeros if we wanted to get it gooder.
Add some more zeros if we wanted to get it gooder. That's right. And this is something where I do a whole bunch of like programming where you have tolerances like this, right? Even just checking equality, because we've noted that you sometimes get some slightly wrong answers, right, out of the computer when you're doing certain types of manipulations of numbers in a computer, and so I can't test to see if two numbers are equal by testing to see if they're exactly equal. I have to test to see if they're very, very close to equal, most of the time, in fact, in most of the work that I do.
Interesting.
So this kind of tolerance is, this is something that comes up a lot in real life.
And I mean, how do you know what kind of tolerance you're working in? I mean, just you need.
It depends. It really does depend on the circumstances. Like,
because I mean, if you're going to have compounding, I won't call them errors because it's not really error, but compounding.
Well, it is error, right? Well, so one of the things about it is you often tend to try to do this equality test at the very end, right? After you're done compounding everything, right? To see if two things, a lot of the time I have to ask if two things are equal, because I have to treat them differently if they aren't, right? It isn't, there's a variety of circumstances where I have to ask this question: are these things equal? And what an appropriate tolerance is dependent. It's contextually dependent. Typically, with the equality testing, though, we're working with a lot more zeros than this.
Yeah, right.
But then you see what they're doing. We talked about this already, but with the square root, right?
we're
The definition
or,
of square root of SQRT, right?
uh,
It's right
this
above
whole thing.
there, right? I mean, you do see that though, right? That's the we talked about the public interface, but I just want to make sure that we're clear on this.
Above it,
Where they define
right here.
square root itself, SQRT. So right above what you have highlighted.
Oh yeah.
Okay,
Uh,
that's all pretty clear, right?
oh, yeah, we didn't. Oh, in terms of getting this started.
Right. We talked about this a little bit, but I'm not sure you were actually looking at this code, or I just want to make sure that you've looked at this and understood what's happening there.
The iter one. Yeah. It's calling the square root iter
Right.
function starting at 1.
Right. It's just so that you don't have to provide a guess yourself.
Yeah. Right. Yep.
Okay.
Yeah, we needed the x, and
Yeah.
we call square root iter with the argument x. Is that the right way? I mean, with the argument with whatever it is that we.
Yeah, we call it with 1.0 as the guess, right? We just want to fix the guess. We're always going to use 1.0. We talked about this. So they have a couple of exercises here, which might be worth looking at for you at some point. We've talked about what's going on in exercise 1.6, and I don't know if you recall that. Might be worth just taking a quick look at it. Do you remember cond? We looked at cond. We've used if more because it's a little bit easier to understand. But do you remember cond?
No, that's different than cons. So.
It is different than cons. We don't have to worry about it at this point. It is. We should go back and look at cond again sometime. Cond is very useful.
Okay.
And in fact, we hadn't looked at cond at the point when we wrote the filter function. But my filter would have been better written with a cond, and I think it might have made it a little bit clearer, because one cond would have taken the place of two ifs, right? You remember how we have a nested if in my filter?
Yeah.
And the cond, a cond might have made it a little clearer that we're just dealing with three cases, right? Cond just allows you to have a conditional that can look at any number of cases and then have a default if, so for each of them, if any of them pass, they're in order. So the first one where the test that you're doing passes, that's what you return. And if you run through all of them, you can have an else there. You can have a default value that it returns if it falls through it all. I don't know if this is ringing a bell or not.
It is ringing a bell. But I think it's ringing more a bell on either on and or.
Okay. Well, right. It's the same reason with this. I mean, we've kind of spoiled this exercise a little bit, but it is the same reason. But let's move on. I think if you don't remember cond pretty clearly, then it's going to be hard to even talk about this. So exercise 1.7, let's at least just sort of look at it. Exercise 1.7 is actually, exercise 1.7 is interesting.
Alternate strategy. Watch how guess changes when there's index in the stop and changes a very small fraction of the guess. It's not a square root procedure that uses this kind of end test. Does this work better for small and large numbers? Okay, so why? So when you're saying of very small numbers, I'm thinking, numbers with a bunch of zeros after the decimal.
Well, let's think about it this way, right? We have this thing in good enough, which is 0.001, if it's within 0.001. Number, right?
Yeah.
What happens if we're looking for the square root of 0.0003?
Yeah, it's already smaller than our.
Well, our guess is going to be 1, so it's not going to be smaller, first of all, right? It's going to be it's going to be vastly larger than that. But the thing about it is that being within 0.001 of the square root of 0.0003,
Mm-hmm.
that's not very accurate in that case, is it?
Yeah.
Right? That
Yeah.
doesn't, we can say, okay, being within 0.001 of the square root of 2 means we're pretty close to the square root of 2, right?
Mm-hmm.
But being within 0.001 of the square root of 0.0003 does not actually mean that we're really all that close to it. Do you see how like accuracy there is sort of proportional to the size of the number?
Yeah. Yep.
And so you see what they're saying about designing one where what you're looking at is how much it's changed in proportion to the number.
I don't see that, but I understand your explanation on the small numbers.
Okay. But do you understand what they're saying about the alternative way of writing good enough?
Are you talking about up in here an alternative strategy? Really good enough to watch how guess changes.
Yes, that one.
When it's going to stop when they change a very small fraction of the guess. Um, it's a very small fraction. So basically, where
Well, so let's can you actually go back up and look at the table where they're actually kind of working out an example of Newton's method?
yeah,
This isn't super critical for the stuff that we're doing, but it's kind of it's a good way. It's useful to pick up ways of thinking about things as you go along, and this is sort of a way of thinking about things that might come in handy for you in a variety of places. So do you see? So we start off with a guess of 1, right?
yeah,
And when we improve that guess, we get 1.5. So
Mm-hmm.
the guess changed by 50%,
Mm-hmm.
going from
Yeah,
1 to 1.5. And then you can look down at like 1.5 changes to 1.4167, right?
yeah,
So now it changed by like less than 1/15th, which is around 7%, right? So it went from changing by 50% to changing to, by less than 7%.
Mm-hmm. Yeah,
And then we went from 1.4167 to 1.4142. I'm not even going to like you see that that's a very small percentage of it that
yeah.
it changed by,
It's thousandths of it. It's like yeah,
right? So there's a pattern here, and you kind of have to know that this does hold true for this kind of thing, that this is a general truth about it. But
yeah.
one of the things we could do is we could kind of we could look at how much it was changing on every step and decide to stop when it just wasn't changing very much.
Rather than yes, we'd have to code in. Um, well, it'd be a whole new different good enough.
It would be, and it would have to take actually different arguments. It would have to take old guess and new guess
Mm-hmm.
as its things, right? You just have to pass it old guess and new guess, and then you would just actually look at the difference between them and see, how large a proportion of old guess and new guess the change between them was.
Mm-hmm.
And by making it proportionate there, you see that it would kind of adapt itself to both smaller and larger numbers, right? Does
Oh, I
that kind
didn't
of make
think.
sense to you?
It makes sense around the larger. I mean, the smaller numbers we were just looking through. I hadn't thought about but although on that good enough, I'm trying to think of like how would you know? I guess you'd want to when your guesses were changing to in some portion smaller than the number itself, than the already small number. You know, like if the number were 0.003 and the change of your guess were 1/100th of that or one whatever, you could have the same kind of tolerance range.
Yeah, I don't
Um,
know that you'd really. I mean, they're not necessarily suggesting that. They're just suggesting that you make it a proportion of the guess itself. But that kind of bakes that into a little bit because your guesses themselves are very small
yep.
with small numbers, right? So if you
Well,
just sort of look at the proportion, I mean, not initially, but they very quickly become very small, right?
yeah,
Okay,
yeah, but the number's already small, so it's kind of I mean, a small number isn't. It's a relation. I mean, it's big to somebody.
it's big to
It's
somebody. That's right. And so this kind of bakes that in, though, right? It bakes in like we're not really dealing in absolutes anymore. We're dealing with something that's relative to the guess. It's proportional to the guess, but the guess itself is going to pretty quickly converge on something that is to some degree in proportion to this, to the number we're looking for the square root of, right?
Yeah. 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 So
Anyway,
you just have set your range. But then in terms of very large numbers, um,
well, we'd give you consistency for very large numbers. This good enough already works pretty well, right?
I would think so. But it says it doesn't. Though. It says you're going to have a problem with very large numbers. Isn't that what they're saying here?
Wait.
Very small numbers often use arithmetic operators. I thought it said this makes okay. In real computers, arithmetic operations are almost always performed with limited precision. Makes our test inadequate for very large numbers.
That I don't think we want to necessarily talk about too much right now.
Okay. Fair enough.
Though, so, and let's see, 1.8. Right. So, do you see what they're getting at with 1.8?
It's based on the fact that if y is an approximation of the true x, then a better approximation is given by the value plus 2y divided by 3. Uses formula in the procedure analogous to the square root procedure. No, I don't.
Okay. So, in 1.7, they're asking you to basically rate a different and perhaps better good enough.
Mm-hmm.
Here, they're asking you to rate something that does the same thing for finding cube roots as this did for square roots. And what you would be changing is basically the improve function, right? Because if you look back at the square root iter, one of the things that you'll note, okay, yeah, there it is. One of the things you'll note about square root iter is that, I mean, you'd want to change the name to like cube root iter, right?
Yeah.
But the only thing that would have to change about this other than that name change would be the improve, right? This is a procedure that improves guesses at the square root, right?
Mm-hmm.
And that's why it finds square root, is because it improves guesses at the square root. That's the only thing that's actually really specific to square roots in here, actually, is that the improves that. But you see how it's an actually pretty generalizable thing. If you have an improve that improves guesses at cube roots, you could use that improve in here, and you would get cube roots out of the other end of this.
Yeah, you just have to but so your average would be a little bit different here. You'd have to write a different thing in here.
Well, you'd have a different improve, right? So if you look back down at exercise 1.8,
yeah,
they're just basically giving you an improve that works for cube roots, right? So
I'm just trying to think of how you write that out. The guess. So this part here would be dividing. So I can. I'd have to type it out.
So I think that might be, if you get a little bit of time at some point during the week, that might be a worthwhile thing to do, which is take this square root iter stuff, all this square root stuff, get it working in Racket, and then write cube root iter as well and see how far you get with that. In fact, I would say that if we weren't stopping at 10, I might actually say maybe we should just do that right now, because I think that you could really use some practice writing code, right? Which we're going to move away from, we're going to switch gears a little bit pretty soon and just kind of go into actually starting to write some programs that do things. Because you do have to write code to learn how to program, right? We've been covering some conceptual ground. Well, it's important to have some tools too, right? Like you need to have some tools to program with. And, but we have enough tools, we'll use some libraries that are built into Racket. And we'll write some little programs involving like images and animation, and eventually even perhaps interaction with that animation. But it would still be good, right now, to have a little experience just sort of trying to turn that into scheme, right?
Yeah.
The
I don't
mechanics
know.
of that. So let's take a look at what they're talking about in 1.18, because they get into some pretty interesting stuff here in a little bit, and I think it might be worth following this thread in SICP for a little bit.
Okay, cool. Procedures of black box. That the square root iter is recursive. That is, the procedure is defined in terms of itself. The idea of being able to define a procedure in terms of itself may be disturbing. It may seem unclear how such a circular definition can make sense at all, much less specify a well-defined process to be carried out by a computer. This will be addressed more carefully. Section 1.2. Oh, not there. But first, let's consider some other important points to illustrate the square root example. Observe that the problem of computing square roots breaks up naturally into a number of subproblems: how to tell whether a guess is good enough, how to improve a guess, and so on. Each of these tasks is accomplished by a separate procedure. The entire square root program can be viewed as a cluster of procedures that mirrors the composition of the problem into subproblems. Good enough or improve. Good enough is
Right. So what we're seeing here is this mirrors some of the structure of the actual code, right? You add a square root function procedure, and it called square root iter, and square root iter called good enough, and it called improve. And improve used average, right, to calculate the average. And good enough used square, and it used abs, right?
Okay.
Now let's note something about this. We could have written out the code for each of these things right in place, right? So square root iter especially, we could have just written it as one big function without calling any other procedures, right? We would have had to write out the code for good enough right in the procedure.
Yeah.
Right?
Yeah. Right. They go on to that was my thing of well, this whole thing doesn't really make sense. Whoops. Because we don't know what good enough is and we don't know what improve is.
Right.
But then we go on to define it.
We go on to define it. And so at the time that we're writing square root iter, we just assume that those things are going to do what we want them to do.
Yeah.
We know that we know how to write those things. So we can write in terms of those things and define them later. And the nice thing about that is we don't have to worry about the correctness of that. We just don't have to worry about the details of it at all at this point, right? We just say, yeah, this procedure does what it says it does. We're just going to assume that it does, right?
Okay.
Fair enough.
Yeah, I mean, I guess so. I mean, me being where I'm at now, I'd want to write those defines first.
I mean, I often do, actually. I often program very bottom up. But here's the thing. In order to know, Alan Perlis said something. I like my Perlisisms. I think I may have mentioned that before. But he said, every program should be written top down, except the first time. So top down is the way that they're writing this here, where they're defining this function square root iter before they define the procedures that it calls, right? That's top down. And you'll note that corresponds very much to the shape of this sort of tree that they're drawing, right? Which is that square root iter is at the top and square and abs and average are at the bottom. A lot of the time, it makes sense to work kind of bottom up. And a lot of the time, it kind of makes sense you kind of alternate styles working towards these. Here's the thing, though, is that you have to know something about how square root iter works to know that you're going to need square, abs, and average, right? So you're at least thinking top down a little bit, right? You kind of have to have that idea at least.
Yeah.
Like, I'm going to need square, I'm going to need abs, I'm going to need average to know what you should be writing bottom up. Now, you may very well, at that point, just go, okay, now I'm going to go write those first.
Yeah.
But the important thing is that when we're writing square root iter, whether or not we've already written these functions or they're just defined for us somewhere, right? Like square, we didn't write. Square is just defined for us somewhere.
Abs is defined too.
Abs is defined too. But Actually, I don't think so. I think what it is that they're referring to procedures that they've already written earlier in the book.
Okay.
Okay. And I don't even know if MIT Scheme had at its top level. I don't know if it had like an abs function, and I'm pretty sure it didn't have a square function. Now, Racket will have for sure an abs function somewhere, right, in a library, but it's probably not just defined at the top level. I bet you if you were to, again, because of lag, I don't really want to switch back to Racket. The lag really is a little bit unfortunate because it'd be very nice to be able to switch back and forth a little bit and play with the REPL. And we may do that a little bit, but I don't want to do it just for the sake of figuring out if abs is there.
We'll just see what, we've got, 4 more, and then we'll be on the road.
Well, it'll be very interesting to see what it's like. You may actually have better internet on the road, though.
Oh, yeah. If you're on the top of a mountain, in New Mexico or something. Yeah.
Yeah. But all right, so let's jump back down to where they're talking about black box abstractions, because they're saying something very similar to what I'm saying here. We're getting at the same thing here. Oh, but I wanted to finish up what I was saying here, and then they'll probably do the same thing, which is, regardless of whether we write square and abs and average first, or we write them after we've written square root iter, when we are writing square root iter, we don't want to have to think about how square and abs and average do what they do.
Mm-hmm.
Right? We want to just say, look, they do what they do. We only want to worry about square root iter and how it works. And this is a lot of the value of pulling square and abs and average out into their own things, is that it limits how much we have to think about at one time.
Yeah.
And this is really hugely important because as you write programs, the programs tend to get bigger and bigger and bigger and bigger. I've worked on programs that had hundreds of thousands of lines of code.
Yeah.
And you can't hold hundreds of thousands of lines of code in your head, right? You just can't do it. You can't understand everything about the system. And so a lot of... I'm sorry?
Well, I was say, yeah, and that totally makes sense. I mean, and I can appreciate how if it wasn't something as basic as square or average, which like I've used those all my life more or less basically, so I already kind of know it. But a lot of your procedures are going to be not as intuitive.
Right. Some of them may do quite complicated stuff, and so when you're using them, though, you just have to assume that they do what they're going to do. And what I'm also saying is this thing of limiting how much you have to think about at once. This is one way of doing that, which is having procedures. There are actually a lot of different ways of trying to limit how much you have to think about at once. And this is a really, really important thing in programming, is figuring out how to have to think about the smallest unit possible.
Yeah.
At any given
point. It kind of
time.
seems a lot of what programming is. I mean, like how computers have, but, from my tiny little sliver of what I just like building up these layers of complexity.
Yeah, that's exactly what it was. And, we talk about these as being sort of abstractions, right? Where you take some big, huge, complicated thing. I mean, average isn't and abs isn't and square isn't. These aren't big, huge, complicated things, but you can imagine that they could be. You could have a procedure that's like some big, huge, complicated thing, and you just give it a name and know what it's supposed to do. And that's an abstraction over the concrete details of what it's doing internally, right?
Yep.
So we build abstractions a lot in computing.
And
that's something that, I could get pretty philosophical about, and I'm gonna not do that at the moment, but I probably will at some point. We'll talk about it.
I'll be talking about that later.
Yeah, I mean, it's important to understand that abstractions have a cost too, right? Every abstraction has a cost, and so you kind of have to assess abstractions in terms of the cost and the benefit, but an awful lot of the time they're hugely beneficial, right? And so pulling things out into procedures is fairly low cost and fairly high benefit, generally speaking. So I tend to do a lot of that. I tend to write, there's something the small talk people used to say, lots of little methods, but they mean procedures basically when they say methods. Lots of little procedures, and I tend to write in that kind of a style an awful lot of the time. I will write a fair number of procedures that are a line long, and you're almost like, the name is longer than the body of the procedure. Why are you doing that? Well, it's because I want to just give it a name and forget about how it does what it does, right? And you can take this too far, but sometimes it's good to kind of write code that reads almost like English. It makes errors very, very obvious sometimes. But anyway, so going below their little tree diagram, which is where you'd kind of gotten to, right?
Important. We could take any large program, divide it into parts, first 10 lines, next 10, so on. Rather, it is crucial that each procedure accomplish identifiable tasks. Module defining other procedures, yeah. For example, define good enough procedure in terms of square, we regard the square procedure as a black box. We're not at that moment concerned how procedure computes the result, only that computes the square. Details of how the square is computed can be suppressed to be considered at a later time. Indeed, as far as the good enough procedure is concerned, square is not quite a procedure, rather an abstraction of a procedure, so-called procedural abstraction. At this level of abstraction, any procedure that computes the square is equally good. Yeah.
So you really don't care what's on the inside of it.
Right? Yeah, I'm just looking for the consistent result that returns it accurate.
Yeah, and speaking of hiding details, one of the things about this is that from the outside, if you are calling something like square, you shouldn't be relying on how it does things either. You want the freedom to change your mind later on and rewrite square, right? And I indeed publish some public-facing APIs. I have code where I am giving it to other people and they call my functions. They call my procedures. And it's important to them that the signature of those procedures not change, right? Because they're writing code against that and they want their code to keep working with successive versions of my API, right? They don't want...
What's API?
I'm sorry?
What's API?
Application Programmer's Interface. So that's where I'm giving somebody... I'm giving somebody a library of code, and I'm documenting what procedures are in that library and what you pass to them and what they return and some other stuff too, like what errors can be signaled from them. And they're writing code that calls my procedures. And so those procedures, that interface makes up an API because they're the application programmer. They're writing their application using my library. Do you see what I'm saying? So they're the application programmer, and that's their interface to my library. And a lot of what I have in, the code that API winds up eventually calling of mine, some of it is extremely complicated code. I can change my mind about anything that's behind that API layer without the people calling the API having to care about that at all, as long as the interface remains the same. These procedures have to take the same arguments. These procedures have to return the same types of values, right? I can't change that interface without breaking other people's code.
Yeah.
So part of the art of designing these APIs is to design it in such a way that it exposes as little as possible about the implementation details, because I want as much freedom to change my mind as I can have in the future while still not breaking their code.
Interesting. Yeah, I guess I can follow that in concept, but I'm kind of like, well, how would you change it without it changing the value, how the interface is, and then if you were, then why would you, like what purpose would it serve if it's still? But I can imagine a little bit, but
well, for instance, I might be doing something down in the guts there, and I might figure out a faster way to do it. Right?
Okay.
A faster way to calculate a result, for instance. And, or I might just be looking at the structure of my code and thinking, there's a way for me to make this code more comprehensible by reorganizing it. So I want to change the way that some of my internal stuff is structured. Right? But I want to leave that interface the same for them.
Yep. I can see that.
Right, and here they're giving an example, which I was about to actually use square as an example. So yeah, they're going exactly where I was going to go with this. This is just another definition of square, another way of squaring numbers.
What's EXP? Define square. I can't remember much. My math is a lot.
Don't worry too much about the details of how their own version it does what it does. Just say, okay, that's another way of writing square.
Yep. Fair enough.
Involving exponentiation and logarithms.
Right. Yeah.
Do you recall what E is? The constant E? Have you? I assume you were
No,
probably exposed to E at some point in school.
you know, no, other than like energy, equaling MC squared.
Yeah,
But
not that E. Not that E.
I didn't think so.
It stands for Euler's number. But we won't worry about it too much. I think it stands for Euler's number. The EI definitely comes from Euler. Euler was a very famous mathematician.
Okay.
In fact, many people would say that probably the greatest mathematician of all time. In fact,
Huh.
so he comes
All
up a
right.
lot. Okay, so we've talked a little bit about this as well before, but let's take a look at local names here. What they're talking about here. Right?
Mm-hmm.
This is an important thing to recognize, which is that these procedures have their own environment, they have their own why,
Yeah.
say, right, and
Yep.
that doesn't affect anybody else's why.
Yep. Simplest consequence. Ames must be local body procedure. Good enough to determine the square of the first argument is within a given tolerance of the second argument. See that the author good enough uses guess to refer to the first argument and x to refer to the second. Argument of square guess. The square used x as well to be different x than the one in square. Oh, right. Okay.
So this bit where they're talking about bound, I'm not quite sure where you are because you were speaking very quietly there. You were sort
Yeah,
of
sorry, I'm
following
almost.
along, but
I'm like, I was in this paragraph, and I'm like, what are they talking about? Oh, they're talking about define square up above.
right.
Oh no, they're talking about.
They're talking about these two different definitions of square where they named the parameter of square, x in one case and y in another. Do you see those two things
Okay, yeah,
right
up
there?
here. That's what.
Okay.
That's what
Yeah.
I thought. Yeah, and the procedure square must not affect the value of x that is used. Yeah, right. They're separate environments.
They're separate environments, right? So
Yeah.
they don't affect each other. But also, if we are calling square, we don't know what the parameter to square is called inside square,
Mm-hmm.
and we don't care. We don't know.
Yeah.
We don't care. We can't know, in fact. There is no way for us to even find this information out if we're calling it, unless we have access to the source code and we can go read it, right?
Yeah.
But
Yep.
if all we have is sort of a compiled procedure, right? If all we have is the procedure object, we can't even find that. I mean, you might actually be able to. It's an implementation detail of Racket, but like conceptually speaking, it's completely
Yeah.
hidden from us, right? Everything inside the procedure is completely hidden from us.
And I would think is irrelevant unless we're trying to change that procedure in some manner, because
Right.
it's only in reference to itself anyways within that specific environment.
Right. But it's a really important thing to understand that thing. And as they say, the consequences are profound. We are just going to look at the tip of the iceberg of these consequences right now. But this is kind of related to what I was talking about. There is this this formalism called the lambda calculus that essentially you can build all of computation out of. And stuff that they're talking about right here is very closely related, actually, to the nature of the lambda calculus. So it really is pretty profound, and we'll take a look at least a little bit of this stuff. I mean, I don't think we want to delve too deeply into the theory of computation at this point, but we'll take a little bit. I think they have a footnote talking about church numerals in here somewhere, and church numerals are at least worth looking at. Not today though.
Yeah. So I shouldn't have. Oh, it wasn't that far away. Wait, we would do. Okay, we're this close. Were you talking about the iceberg and profound? Is that in here somewhere? Where am I?
They say that the consequences are pretty profound somewhere.
Okay.
Somewhere in here.
Squares.
It's consequently right. Between the definition of the squares and good enough. It's above there. They're saying, right, that the meaning of a procedure should be independent of the parameter names used by its author, that this seems on the surface to be self-evident, but its consequences are profound. And I'm just kind of saying, yes, we're only going to look at kind of the tip of that iceberg at the moment. But there's some terminology down here that's kind of important. So they're referring to what we've kind of informally been calling arguments. They're saying, they're naming them formal parameters, right? They're being quite precise about this.
Okay.
And what they're saying is that such a name is called a bound variable, right?
Illustrates another way in which we would like to control the use of names.
Okay, but up above there, I think you skipped over like a fairly important bit up here, right? So one paragraph above that.
Okay.
There's some terminology that they're introducing here, and I think we want to look at this terminology, right?
That it doesn't matter what name the formal parameter has.
Right. We don't care if it's X or it's Y.
Yeah.
But it's this bit that's kind of important, which is such a name, the name of, say, a formal parameter, is called a bound variable.
Yep.
And, we've talked about bind. We have used that word quite a bit, right? It binds its formal parameters. It binds them to a value.
Right.
And if we take a procedure and we change the name, as long as we change it everywhere within the procedure, it will not change the operation of that procedure.
Mm-hmm. If a variable is not bound, we say it is free. So there hasn't been defined.
Well,
but then it's all.
Here's the thing, though. It could be bound in the enclosing scope, right? Do you remember how we defined pig to be 42?
Mm-hmm.
So if you then write a function that refers to pig, it's not going to be an error. It's going to, remember we talked about environments kind of nesting like Kachinka dolls, right? Like the Russian dolls, right? But from the point of view of that procedure, pig is a free variable. It is not bound within the body of the procedure itself. It is a free variable.
Yep. Okay.
So it's not an error to refer to that particular free variable. But it will be an error if the procedure is not within an environment that has a binding for that name, right? Does that make sense?
It will be an error if the procedure is not within an environment that has a binding for that name.
Right. Like we defined pig, and then we could write a procedure that refers to pig, right? That name pig. Mm-hmm. And that's not going to be an error if we defined pig. But know now that we cannot tell just by looking at the procedure whether the procedure is going to error or not, right? We have to know about the enclosing environment to know if the procedure is correct or not at that point, right? Are you following?
I don't think we have to know in the enclosing environment, but it couldn't just be. I mean, if it just referring like X in in defining square X here, no, maybe
well,
I'm
that's
not
not a free variable. X is not a free variable there. X is a bound variable, right? So we know that referring to X is not going to be an error there in the sense of it being undefined, right? We know X is defined because it is a formal parameter of the procedure. It's going to be an error if you try to call square without something for X, right? That's a different error. We know that it's safe to refer to X. X will have a binding there. It always will because it is a bound variable, which is what they're talking about. But, here, let's actually jump back to Racket for a minute, lag or not, because I want to be clear about what I'm talking about here.
It didn't have to. It'd be lag, I'll maximize.
Yeah. It's just there's the lag switching windows. It's every pixel on the screen changes, and so it lags really hard typically for a second. But it's fine, because I do think we want to be clear about this, and this is hard to explain without an example.
Yeah. So what is free variable there? I guess
maybe jump up into the top and define pig. In the top, just define pig to be 42, like we did before. Okay. Now, so again, up in the top, like, write a procedure and call it like good pig, right? Write a procedure named good pig and just have it print the value of pig. So remember the special syntax for defining. Procedures using define.
Wait, what are we doing? We're doing a procedure.
It doesn't take any arguments. Yeah. Doesn't need to. Okay. Okay, but it does need a body. So if you go in there, why don't you hit return, right? So that it's not all on one line. Open up a paren and just call print line with pig, with the name pig. Nope, not the string, the symbol. Yeah. Okay, so why don't you run this? Like run, hit run. And now from the REPL, call good pig. Okay. So pig is a free variable within that procedure, right? It's not a formal parameter.
Within this one up here?
No, within good pig, within the procedure that we defined.
Okay.
Right? That use of pig there, it is a free variable within the procedure pig, right?
Within the procedure good pig.
Good pig, within the procedure good pig, right? That's a free variable, right? It is not bound within pig's environment. It is having to reach out into the enclosing scope to get it.
I gotcha.
Okay. Now, why don't you define bad poke? Define a procedure called bad poke, and do the same thing that you did there, except instead of printing pig, print poke. Okay. And now run it and try calling bad poke. Oh, well, it won't even let you. Okay. All right. Yeah. Some languages would allow you to do that and wouldn't error until you actually
got it.
Tried to call it. So
because it was a string, I'm trying to use poke as an argument.
It's not an argument, but you're trying to refer to it. It's not defined, right? It's a free variable. So it goes and it starts looking for a binding for poke. And first it looks in the environment of the procedure itself, right? Mm-hmm. It says, okay, no binding for that. And then it looks in the outer scope, right? The outer environment. And in that outer environment, pig is defined, for instance, which is why good pig worked.
Yep.
But poke is not defined there. So it runs out of environments to look through. It is popped up all the way through the nesting dolls. In this case, they're not very deeply nested.
Right.
And it couldn't find it. And so this is an error. So what I'm trying to say about this is something to remember about free variables is if I write square, right, define square of x, x times x, I can look at square and I can say square is correct. Right?
Okay.
I can look at it. I can just look at it. I can't tell if I use a free variable in a procedure, I can't tell if that procedure is correct without understanding what the environment that encloses it is. Because it's not a correct procedure if it's referring to something without a binding. If it has a free variable, and that variable is not bound within the enclosing scope, then the procedure is not correct. So we'd really like analysis of correctness to be as local as possible, right? Mm-hmm. If we're writing a procedure, it is a very desirable property that we can look just at the text of the procedure and be able to determine whether or not that procedure is correct.
Mm-hmm.
So free variables, which can be very useful in certain cases. Okay? This is not to say that one should never use a free variable in a procedure, but note that they have this drawback, that they reduce locality.
Mm-hmm. Okay.
Okay.
So it's a free variable only within this I mean, this pig here is a free variable, but this pig up here is not, right? Because it's, are you seeing, I can see if you can fit a
Well,
line for,
I mean,
oh,
there it's in a define, right?
I just have to
So,
point out that our defined pig 42 ended up being on line 42.
yeah,
Sorry.
there you go. Well, maybe this indicates something deep about the meaning of life, the universe, and everything. I mean, here's the thing: within a define is a special form itself.
Yeah.
We're not looking for a binding for pig there, and pig is not the parameter of anything there, right? I wouldn't get too hung up on this, but note that it's just a completely different context. What we're talking about does not apply when you're defining a symbol there, right?
Okay. Okay.
Pig as a symbol is always a perfectly valid symbol. The question is, does pig have a binding when we use it in a case where we need to use its binding, right? Within that define, we are not, pig doesn't have a binding before we define it. It doesn't matter. We're not trying to find the value that pig is bound to there, right? Define is a special form. It just like does its own special magical thing.
Yeah.
We're really talking about procedures here, not special forms. And remember, special forms are not procedures. Special forms have their own rules. They're magic.
Right.
So anyway, let's just jump back to SICP. We've got about 20 minutes left. So, but yeah, I did want to be very, very clear about this bit about there are some very interesting free variables wind up having some very interesting properties related to environments that we will take a look at. So
The set for expressions for which a binding defines a name is called the scope of that name. And procedure definition. The bound variables declared as the formal parameters of the procedure have the body of the procedure as their scope.
right. So
Body of the procedure. Yeah. Okay.
let's think about that, right? When we write square and we say x and we bind, somebody calls square with a value for x. X is bound to that value, but over what locale is x bound to that value, right? Where does that binding? Where is that binding? Where does it exist, right?
Yeah, within the procedure itself.
Within the
because
body of the
that's
procedure.
what we're
Specifically within the body of the procedure, right?
right. Not the argument list.
Not the argument list. It's within the body of the procedure.
Oh, well, isn't it the argument list too? Because I mean, it's if X is the argument list, we're kind of replacing out the 5 or whatever the in this case an integer.
No, because the argument list is not really something that exists at the time that the procedure is being called. Again, I wouldn't worry too much about this, but just kind of just take it on faith at the moment that it doesn't even really make sense to think about it that way, right? Like the scope is the body of the procedure.
Yeah. I understand that's where the work is being done.
Well, it's also really where the scope of that binding exists. That this binding doesn't exist until you actually call the procedure, right?
Mm-hmm.
Because if you call it with 5 once, it's going to bind x to that 5. If you call it with 7 another time, it's going to bind x to that, right? It isn't until you invoke it and you actually give it a parameter, right, for x to bind that the binding happens, right?
Mm-hmm. Okay.
And again, we're sort of dealing with special forms here. We're either dealing with lambda, or we're dealing with define, which is it's a special form of its own and is syntactic sugar over lambda. So again, that's the kind of thing where special forms are sort of magic, right? Special forms are doing their own thing, and the nature of the argument list within lambda and within this special syntax for define, kind of doing its own thing. I think maybe we'll just leave it at that for the moment.
Yep. Well, guessing extra bound variables, but are free. Goodness, should be.
In this sense, you have to use lots of free variables, right? You want to call other procedures. And in fact, even square, for instance, right? Note that square has that times symbol in it, that star, right? That star itself is a free variable, right? Which is what they're getting at.
Yeah, okay. Sure.
However, it's a lot more common to I mean, because you have to do that to call other procedures, like, this is a little bit different than having free variables that aren't sort of known procedures, I guess. Like, this thing of calling other procedures
Yeah.
is a bit of a special case of free variables.
Yeah. I mean, they're known. They just are free within the context of that procedure. I mean, known meaning like they're defined.
They are. Well, and the same thing could be said of pig when we called it in good pig, right? It is. And you can certainly do that kind of thing. However, it is something that you typically do a lot of when it comes to procedures, because you do want to call other procedures that are, that are free. And it's something you tend to do less of with things that represent values other than procedures. But you do sometimes do it with them as well, in specific cases. So, and we'll see some of those.
Yeah.
And that thing that they're saying in parenthesis is kind of important, right? If you renamed
What
gets,
if?
if we renamed
Yeah,
gets
this is.
abs, okay,
Sorry, I'm very late.
you broke.
That's like we were talking about.
Yeah, stepping on names. You have to be somewhat careful about stepping on names. Now, there are times to want to shadow names. There are times that you actually want to shadow names, but you only want to do it intentionally, right? Doing it unintentionally can lead to pretty catastrophic consequences. But they're also making another important point, which is that you can change the names of any bound variables as long as you change them consistently throughout the function, right?
Mm-hmm.
You can't do that with your free variables. They're making a point here that if you changed, cos stands for cosine, right?
Uh-huh.
So if you put cosine there in instead of abs, you can't change that name even if you change it consistently within the procedure, right? Because cosine is defined outside of the procedure, and you probably don't want a cosine where you expect it in abs, right? So they're just making that point here.
Yeah. You'd have to reach to that thing and redefine out there, which in this circumstance you wouldn't want to do because, well, I mean,
yeah. So here, they're kind of pointing something out here that I'm going to kind of gloss over this a little bit. You may want to come back and read this because they are very precise about things, and that precision is kind of useful. They're more precise than I'm going to be speaking extempore, right? But note that we defined all of these functions at the top level, and they're going to introduce something that we haven't talked about yet, which is that you can put defines inside of defines, right? Only when you're using the special syntax for procedures. But do you see how they're actually nesting? They're using defines actually as part of the body, essentially, of a procedure. Do you see what they're doing there in terms of moving those definitions inside square root?
Oh, in this one down here? This one doesn't.
I don't know. Are you highlighting something, or I can't see your pointer?
Oh, you can't see, but you see the highlighting, can't you?
I can see the highlighting.
Have I been highlighting?
I just can't see your pointer. Yeah. So I was in that first block, right? Like, they define square root, and then they close up all the parentheses of square root, and they begin a new line, and they define square root iter, and then they define good enough, right? These are all at the top level, in the top level environment. They're being defined. However, when you look down at the next block of code there, you'll see that they haven't even written the body of square root yet, right? Let alone closed its parens. They're putting these defines inside square root.
Oh, yeah. Okay, that's following. Where are the parens getting closed? So this is something where the indentations should tell me something that I'm probably not picking up on very well in relation to the parens, right?
Right. The indentation should sort of tell you that So they have the argument list. They have define, and they have then the argument list. And then they have a whole bunch of define forms that are at basically the same level as the body.
Yeah, which is, I guess, these three right here.
Actually, it keeps going. Like that last
right.
define keeps going.
Uh,
Is that if? Its body is that if, right? So you have a bunch of procedures defined inside this define.
Mm-hmm. And that's kind of like what you were talking about before. You could just write it rather than, they have it broken down. Now we'll go and define improve, and now we'll go and define good enough and stuff, but they just have it all here. And
well, there's an important consequence of doing this, okay? Just like the names of formal parameters aren't visible from outside it, right? Like if I'm outside square, I can't see the X that's inside square. I have no access to it, right?
Mm-hmm.
It's hidden from me behind, the interface of square, basically. It's part of the machinery. The same thing is true here. If you define, like, good enough here, you can't then at the top level go and call good enough. That name is not visible to you.
Yeah, okay,
That name scope is basically the body of this define.
It's only in relation to square root X. Yeah.
So I'm hiding these names, and this can be useful for a number of reasons. One thing is that it means that there's a lot less likelihood of name collisions.
Mm-hmm.
So I could write some other function other than square root, right? So some other procedure. Here we're basically defining square root, but we're defining also these sort of sub-procedures that square root needs to call. I could have a different thing that had a different good enough, right?
Yeah.
And and again, if it was defined inside these defines, these wouldn't conflict because they're within their own scopes here.
Mm-hmm.
Okay.
Yeah, and that may be a term that is especially useful to me, within different procedures, like just as, kind of to maintain my own internal logic within a given procedure and then within another given procedure and that type of thing. So I don't want to have it defined in the outside environment.
Because we might write cube root as well. Remember how we said that the only thing that you really have to do to turn like square root into cube root is change the improve definition, the definition of improve.
Mm-hmm.
So one thing you could do is you could have one procedure that was called improve square root guess, right? And then you could have a different procedure that was called improve cube root guess, right? Mm-hmm. But if we're nesting these things, we could have a cube root defined with its own internal definitions, and it could have its own improve. And these two names wouldn't step on each other.
Yep.
And so they're just talking about that this is called block structure. And
simple name packaging problem. But there's a better idea lurking here. In addition to internalizing the definitions of the auxiliary procedures, we can simplify them. Since X is bound in the definition of square root, the procedures good enough, improve, and square root iter, which are defined internally to square root, are in the scope of X. Thus, it is not necessary to pass X explicitly to each of these procedures. Instead, we allow X to be a free variable in the internal definitions as shown below. Then X gets its value from the argument with which the enclosing procedure square root is called. This discipline is called lexical scoping.
Yes. So you remember, we ran into this before, which is that when we were, right, that we had to pass this extra X along all of the time.
Yeah.
And you remember how I was saying, well, if X were defined outside at the top level, for instance, we wouldn't have to do this, right?
Yeah.
But we have pretty good reasons for not wanting it to be at the top level. Right?
Yeah.
So we do not want to be reaching out to the top level to get the value of X. Among other things, other procedures could change that value of X on us. We have no way of knowing if they have or not, right? Like, it's just a bad idea to have that X out there at the top level. We would call that kind of a global variable in a lot of cases, is what that's called. It's global. It's visible to everything. But here, this is a very different situation, which is that we can see the entire extent of that X, and we can see everything that can operate on that X. Remember, nothing else on the outside of this define has access to that X, right?
Sure.
So we know nothing else can change it on us. It's safe, and this is sort of what I was talking about this is a case where you really want to use a free variable instead of having something be a formal parameter, right?
Mm-hmm.
That this nesting, this block structure, can do this. Now, what they're saying about this discipline is called lexical scoping. So, lexical scoping, almost every programming language that you're going to run across these days essentially uses lexical scoping. Python has some kind of funny scoping rules, but we won't get into that. And for the most part, it's pretty close. It's pretty close. Python actually really does have wacky scoping, though. Lisps, though, before Scheme, and pretty much all Lisps now, all modern Lisps use lexical scoping as sort of the default rule for scoping. But they used to have a different kind of scoping, like dynamic scoping, used to be sort of the norm in Lisps, where you can see that this scoping, the reason that they're saying it's lexical scoping, is because it's based on the text of the program, right? The X is defined based on like where it is in terms of enclosing parentheses, essentially. That's what determines the scope of X.
Mm.
There's another alternative here, and this is a little hard to wrap your head around, perhaps. You could also base it on the calling of procedures, so that if you called a procedure, say with the formal parameter X, all the procedures that it called could have that X be visible to them. And maybe we won't talk too much about it past that, but note that that's no longer based on sort of the text of the program. That's based on the sequence of procedure calls. And it's something that can actually be very useful in some cases. There are some times when...
Well, so if the X is present in the, what's it called, the formal procedure, then each time it's called, you don't need to call the X again because it's already.
I don't know. You're mixing terminology up here a fair bit to the point where I'm not quite sure what you're getting at, to be perfectly honest with you. And I'm probably not doing a very good job of explaining dynamic scoping. It's a little bit hard to explain without an example. And again, it's a little tricky to switch back into Racket and I can't type. So I'm kind of thinking about how to address this. Let's just say that I'm kind of trying to get across the point that the scoping here, what determines where the visibility of a binding has to do with the text of the program, right? So we have this defined. You can think about it as being like, essentially, we have a procedure and it's defined within sort of, you can think of it as being textual, right? It doesn't have anything to do with the runtime behavior of the program. It's about how the program is written down before you run it.
Mm-hmm. Okay.
That is not the only That is not the only way to scope things, and we will eventually talk about dynamic scoping if we keep doing this long enough. Especially because we'll take a look at at closure, which allows you to have a form of dynamic scoping selectively, and it can be very useful for certain types of things. What people discovered about dynamic scoping, though, is that dynamic scoping becomes quite confusing if it's all that you use, if it's what you always use as your rule for scoping. So Scheme is basically the first Lisp to have lexical scoping. And pretty much all of the other Lisps soon adopted this. All modern Lisps have it. However, there is, for instance, a scripting language inside of Emacs, which is the text editor I use, called eLisp. And eLisp still basically has dynamic scoping. It's a little more complicated than that. But and it's something you really have to be aware of when you write it. However, for the most part, you're not going to run into dynamic scoping all that much anymore. Right, it's not a common feature of programming languages at this point.
Okay. Yeah, I forgot. How old is Scheme? It's pretty old, isn't it?
Well, Lisp is really, really old. Lisp is one of the oldest programming languages. Like Fortran is just slightly older, and of course, we talked about assembly languages before, right? I don't know if you recall talking about assemblers.
Confusing assembler, I think, but compilers.
Okay. Yeah. Assembly languages were the first sort of programming languages, and we talked about this a little bit. Assembly languages have pretty close to a one-to-one. I mean, it's more complicated than that. I'm oversimplifying, but let's just think about it in this oversimplified way. Assemblers, and early assemblers, this was really true of, they had pretty close to a one-to-one correspondence between sort of instructions in assembly language and the instructions on your actual chip, right? Every particular chip, the CPU that runs your computer, has a set of instructions that it can perform. And, when the very first computer programs were essentially written as sequences, the very first digital computer programs were essentially written as sequences of zeros and ones. You're just literally typing out zeros and ones. Not even really typing, probably, but somehow entering zeros and ones. And that's obviously extremely difficult to do correctly. So assemblers were the first thing that came along, where you start assigning mnemonics to the various instructions in your computer. But then higher level languages came along. And, Fortran is a very early programming language. So is Lisp. And Lisp goes back, I think, to 1958, So old. Scheme is more recent, and I do not recall exactly when when the first spec for Scheme came out. Significantly later than 1958, though. I don't know. I'm thinking sometime in the 70s. We could look it up at some point. Be good to know.
Yeah, it was still a while. Still quite a long time ago.
Oh, yeah. A very, very long time ago.
Yeah.
And Scheme has gone through a number of revisions, right? Like R4RS was, I think, the revision that was current at the time that SICP was written. It's basically version 4 of the Scheme specification. Scheme is an actual, has a formal specification that is controlled by a standards body. I believe it's an ANSI standard. Common Lisp is as well, but I think Scheme is an ANSI standard as well. So there's an actual formal standard for Scheme that, there really can't be any disagreement about what the governing document for Scheme is. It is that spec. That's not true of all programming languages, but it's true of Scheme and it's true of Common Lisp. That there is a formal standards body that is in charge of the spec. And so R4RS, there's, I think we're on revision 6 of Scheme. I don't actually do any Scheme programming, to be honest with you. I do some programming in other Lisps. But we're doing Scheme because Scheme is actually really nice for some of this stuff. It's a very small, simple language, especially R4RS Scheme, which is really what this is written in.
Cool.
So let's see. It is 10 o'clock. So you have to go. Well, this was good. I think, this is useful. I think we'll probably want to keep looking at SICP for a little bit. And then, because a lot of, what they're talking about here is really important stuff. And they do a very good job of it. SICP is a good book. And I do want to... I'm sorry?
Well, I was going to say, I'll take a look at some of this stuff too. I was going back and look at some of these earlier pieces a bit, either yesterday or the day before, but just need to chunk out myself a little bit more time.
Yeah, I think that it would be very, very useful for you to actually, sit down and really, really read through SICP, at least up to the point where we were at, and you can keep going if you want to.
Yeah.
I think some of the stuff that they talk about from this point, I think some of it is should be pretty comprehensible for you at this point. And then you may hit a point where it starts getting to be a little bit tough going. But I think you should be able to go further if you'd like. And the other thing is I would take a look at the exercises. You might try out that one, especially with doing the cube roots. See if you can do that one. I think that would be pretty useful. And they also just go over some ideas we've talked about, but they come at them from a different angle. And sometimes having that reinforcement can be very useful, seeing something explained a different way. And yeah, we'll keep going with that a little bit. And I would also like to... So Scheme is a very small language, but Racket is an implementation of Scheme that has a whole bunch of stuff beyond what's in the spec, right? Racket has many, many, many libraries available.
Libraries of what?
Libraries available, right? Libraries that do a lot of things. It has a lot of features that are not part of the base specification of Scheme.
Gotcha.
This is kind of what happens with small languages, is that if you have a small language, you will have a large library for it. Right? Either you'll have to write that library yourself or somebody else is going to write it and provide it. And whether, I kind of call, their languages like Common Lisp, for instance. Common Lisp is a kitchen sink language. So is Python, because the standard library for Python is fundamentally part of the language, right? It's called a library, but it's part of the language. And they have a whole bunch of stuff that's just sort of built in that's always there with the language. And, they're kitchen sink languages. Whether kitchen sink languages are better or these very small languages that you then have to like add a whole bunch of libraries to, when you want to actually do real work, you're going to need libraries. Like if I want to say, go out and get the data from a web server, for instance, right? I don't want to have to write all the code to do that myself. I'm going to want a library that does that for me, right? If I want to interact with the file system in complicated ways, I'm going to want a library that does that. And so Racket has a whole bunch of libraries that allow you to do things, and some of them are designed sort of for teaching purposes. And in particular, they have a library that sort of deals with manipulating images, and that can then be used to create animations from those images, and that can even be used to create interactive programs. Where a user can interact using the mouse and keyboard, etc. And so at some point we'll turn around and start actually trying to write some stuff that does some stuff, right?
Yeah.
Because this has all been very theoretical so far.
Yeah, that's good.
Okay. All right, cool.
Yeah.
Well, have fun, and I'll talk to you next week if not before.
All right. Yeah, perfect. Sounds good.
All right.
Thanks, sir.
Thank you. Have a good one.
Bye.